Imagine for a moment a master architect designing something strong enough to support your entire body, flexible enough for, I don't know, a gymnast, and resilient enough to last a lifetime.
Sounds pretty impossible, right?
Exactly. But that's precisely what you carry around every single day, your spine. Um, Most of us probably don't give it much thought until, well, until it starts to complain.
That's usually how it goes.
But it truly is an engineering marvel. Today we're taking a deep dive into the incredible, often unseen mechanics of your back. Specifically, its intricate musculature,
Yeah.
the vital thoracolumbar fascia, the essential ligaments, and those remarkable shock-absorbing intervertebral discs.
Yeah, all the key players.
We've got a fantastic stack of research here, and honestly, it offers a truly comprehensive and fascinating look into these structures. It really peels back the layers,
Yeah.
in a way that's both detailed and incredibly clear.
It's good stuff, really lays it out well.
So our mission today is to unpack these components, showing you how they work together as one seamlessly integrated system.
Right, not just isolated parts.
And what surprising insights the material reveals about their intricate function and, frankly, their immense importance to your everyday movement and stability. Think of it as exploring the dynamic, sort of self-repairing suspension bridge that is your backbone.
That's a great analogy, actually.
Okay, so let's start with a structure that sounds complex, I admit, but is absolutely pivotal. The thoracolumbar fascia, or TLF. What exactly is this fibrous tissue, and why should we care about it?
Well, the thoracolumbar fascia, it's essentially a dense, multi-layered web of collagen fibers. Think of it like a kind of natural corset around your lower back.
A corset. Okay.
Yeah, and the research we have shows it's not just one simple sheet. It has 3 distinct layers, and each one has its own crucial role.
The layers.
You've got the posterior layer, which is the strongest. It sits right on top of your deep back muscles.
Okay.
Then there's the middle layer. This one acts like a divider, sort of separating those deep back muscles from another important core muscle called the quadratus lumborum.
Quadratus lumborum.
Mhm.
That helps stabilize the pelvis, right?
Exactly. And finally, the anterior layer. It covers the front of the quadratus lumborum. It might be thin, but it's surprisingly robust and forms a key arch near your ribs.
Wow. So it's not just passive tissue. It's a multi-layered strategic structure. What's the most maybe unexpected thing about its role in the back beyond just covering muscles?
I think the key takeaway is that its functions are incredibly dynamic. I mean, beyond covering and compartmentalizing muscles and providing attachment points, it's a crucial system for transmitting and directing forces through what's called dynamic tension.
Dynamic tension.
Yeah, it's a finely tuned sail almost, where tension applied in one area helps stabilize or even move another area.
But this idea of an integrated system really changes how I picture our body's mechanics. The research mentions how muscles we normally think of as hip, pelvic, or leg muscles can interact with arm and spinal muscles via this fascia.
It's truly remarkable, yeah.
Can you elaborate on that, like the practical implications of this load transfer between, say, the legs and the arms?
Absolutely. This fascia plays a pivotal role in allowing for effective load transfer between your spine, pelvis, legs, and, yes, even your arms. It actively connects upper body movements to lower body stability and vice versa.
So it blows apart that old idea of isolated body parts working alone.
Totally. It highlights how forces are seamlessly distributed throughout your torso and limbs. So when you lift something heavy or throw a ball, this fascia is helping to coordinate and distribute those forces across your entire body. Makes you stronger, more stable. The material really emphasizes this whole body connection.
And that dynamic tension concept you mentioned, particularly in the posterior layer, with its crisscross arrangement of fibers, like those connected to the gluteus maximus, your main buttock muscle, and your latissimus dorsi, that big back muscle. How do they create this tension, and why is that so important for stabilization?
Okay, think of those crisscrossing fibers as reinforcing straps. When muscles like your gluteus maximus and latissimus dorsi contract, they pull laterally sideways on this fascia. This pulling action creates what's called an extension moment on your lower spinal processes. Basically, it helps to straighten and stabilize your lower spine.
Oh, okay.
And what's even more intriguing is that this fascial tension isn't just local. It also transmits tension between the bony projections of your lower spine and your ilium, that's the large upper part of your hip bone.
Got it.
This profoundly aids in the stabilization of your sacroiliac joint, the SI joint, that crucial connection between your spine and your pelvis.
Wow.
It's a beautifully efficient way to distribute forces and enhance stability across multiple joints, all at the same time.
So it's almost like a natural internal bracing system, enhancing
Yes.
strength, making muscles more efficient.
Exactly.
And the material even refers to a hydraulic amplifier effect in relation to the TLF. How does a fibrous tissue achieve that? That sounds pretty wild.
It does sound wild, but it's a fantastic insight from the research. The thoracolumbar fascia essentially surrounds your deep back muscles like a tight sleeve or a retinaculum.
Like a sleeve. Okay.
So as these muscles contract and, bulge or expand, they are braced by this fascia. This bracing action increases the pressure within the muscle compartment, much like how a hydraulic system works. And this pressure enhances their power and strength.
So the fascia itself makes the muscle stronger.
In effect, yes. What's fascinating here is how this seemingly simple fibrous tissue acts like a force multiplier. It makes your muscles more effective and powerful in their actions, all without being a muscle itself. It's truly a marvel of biomechanical engineering.
Okay, moving from the fascia, this dynamic web, to the actual engines of movement, the muscles themselves, the material categorizes them into extrinsic and intrinsic. Well, let's start with the extrinsic muscles. They're generally more superficial, right? What's their main gig?
Yeah, the extrinsic back muscles are indeed more superficial. Their
Right.
primary role is largely to connect your trunk to your limbs.
Okay, connecting things.
Think of them as the muscles that move your arms and shoulders, but they also lend some support to your spine. The superficial layer includes muscles you're probably familiar with, like the trapezius and latissimus dorsi.
The big ones, yeah. Lats and traps.
Right, those you use for pulling and shrugging, along with the levator scapulae and the rhomboids, which help control your shoulder blades.
Mm-hmm.
Then a bit deeper, we have the intermediate layer, the serratus posterior, superior, and inferior.
Stratus. Okay.
These are believed to assist with breathing, kind of helping to elevate or depress your ribs. And they also provide proprioceptive input.
Proprioception, that's the body's sense of where it is in space, right? Unconsciously.
Exactly that, your body's awareness of itself.
But the intrinsic muscles,
Yeah.
these sound like the deep, powerful core of our back's stability and movement. The true spinal engineers, maybe.
Absolutely, you nailed it. These intrinsic back muscles are the true workhorses for spinal movement and stability. The research first highlights the erector spinae muscle group.
Erector spinae. Heard of those.
Yeah, they're a powerful group. They form 3 vertical columns running along your entire spine from your lower back, across your rib cage, right up into your neck and the base of your skull.
Wow, the whole length.
Pretty much. They share a common origin point down low from your hip bones and lower spine, which really underscores their unified, powerful action in helping you stand tall, extend your back, and stop you bending too far forward.
Keeps us upright.
Essentially, yes. Beyond the erector spinae, there are other important intrinsic muscles like the interspinalis and intertransversary. They handle smaller, very localized movements and help with fine-tuning spinal control.
Okay, the smaller adjustments.
Then we delve into an even deeper layer, the transversospinalis muscle group. This group is incredibly important for precise spinal. Yep. It includes the semispinalis, which crosses about six vertebral levels, so it spans broad sections of your back and neck.
6 levels, okay.
Next, the multifidus. This one crosses maybe 2 to 4 vertebral levels, providing more localized control.
Multifidus. Important for stability, I hear.
Very important. And finally, the rotators. They cross just 1 or 2 vertebral levels, very small, allowing for really precise segmental adjustments between individual vertebrae.
Tiny little adjustments.
Exactly. So if we connect this to the bigger picture, you can see how these different groups crossing varying numbers of segments work together,
Like an orchestra.
Kind of. While the erector spinae provide the, let's say, brute force for big movements, these smaller, deeper transversospinalis muscles are like your spine's precision engineers, constantly making micro adjustments. It's this beautiful partnership between power and finesse that keeps your spine strong, flexible, and responsive to every single movement you make.
Okay, beyond the muscles and that dynamic fascia, our spine also relies on incredibly strong yet flexible supporting structures. The unsung heroes, as you called them earlier. Let's talk ligaments first. What are their main jobs?
Ligaments are indeed the unsung heroes. They provide robust stability and make sure your spine moves within safe limits. The material lists several key ones.
Lay them on me.
Okay, we have the anterior longitudinal ligament. Runs like a thick band down the front of your spine, all the way from your hip bone to the base of your skull. It stops you from arching your back too far.
Prevents overarching. Got it.
Then, the posterior longitudinal ligament. This runs along the back of the vertebral bodies, but inside the spinal canal. From the lower spine up to the second neck vertebra.
Inside the canal.
Yep. Helps prevent too much forward bending and can protect against disc herniation.
Important then.
Very. Then there's the ligamentum flavum, a remarkable structure connecting the bony plates, the laminae, at the back of each vertebra. It's notably elastic.
Elastic. Like rubber band?
Almost. Allows for flexibility while still providing strong stability, like a bungee cord for your spine.
Cool. What else?
Further down the list, we have intertransverse ligaments connecting the bony side projections.
Transverse processes.
Right. Then the interspinous ligaments connecting the pointy projections at the back.
Spinous processes.
You got it. And the supraspinous ligament, running along the very tips of those back projections. And of course, the neutral ligament up in the neck region.
So their main role overall.
Their overarching role is critical. They act as crucial stabilizers and limiters of excessive motion. They ensure our spine moves within safe functional ranges. Without them, things would be, well, chaotic.
Okay, ligaments as stabilizers. Now let's get to the intervertebral discs, often just called discs. These are so vital for flexibility and shock absorption. The research gives us a deep dive here. How many are there and what's their big job in our suspension bridge spine?
Right, the discs. There are 23 intervertebral discs in total, quite a few.
23.
Yeah, and it's worth clarifying there's no disc directly between the very top neck vertebra and your skull, or between C1 and C2, the first two neck vertebrae, and none within your fused tailbone, the sacrum.
Okay, good clarification.
These discs are incredibly significant. They make up a substantial chunk of your spine's height, somewhere between 20% and 33% of it, actually.
Up to a third?
Can be, yeah. Their big job is multifaceted. They bear and distribute loads, acting like tiny, super-efficient liquid cushions.
Hydrostatic pressure distributors, the text called them.
Exactly. They also allow for multidirectional motion, granting multiple degrees of freedom to the spine. And critically, they restrain excessive motion, providing essential stabilization. Load bearers, movement enablers, stabilizers, all in one.
Let's zoom in on their structure. It's not just one uniform cushion, right? We have the gelatinous nucleus pulposus and the fibrous annulus fibrosus working together. How do they collaborate? Sounds like a fancy donut.
Huh. That's actually a pretty good analogy, like a jelly donut. The nucleus pulposus is described as a gelatinous mass. It's remarkably watery, like 70–90% water.
Okay.
And it's located centrally within the disc, mostly. Its main role is to allow for uniform distribution of pressure within the disc because it's only slightly compressible itself. Yeah. When pressure is applied, say, from jumping or lifting the disc as a whole, kind of bulges outward, distributing that force evenly.
Spreads the load.
Precisely. Surrounding this nucleus is the annulus fibrosus. This is composed of concentric rings of tough fibrocartilage, and its collagen fibers are uniquely arranged in this crisscross pattern.
Crisscross. Why is that important?
That specific arrangement is what allows it to powerfully resist compression, bending, shear forces, and twisting or torsion, while also permitting that essential bulging of the disc underload, protecting the inner nucleus.
That's tough.
Very tough. It's firmly attached to the cartilaginous end plates above and below, and interestingly, only the outer rings of the annulus actually contain blood vessels. Meaning its healing capacity can be quite limited if damaged deeper inside. Not much blood supply there.
Okay. And what about these cartilaginous or vertebral end plates? The research describes them as part of the disc and even mentions something called Schmorl's nodes. What's that about?
Right, the cartilaginous or vertebral end plate. It's essentially a layer of hyaline cartilage covering the top and bottom surfaces of the vertebral bodies. And yeah, many do consider it an integral part of the disc structure itself.
Part of the disc system.
Exactly. It has less water content compared to the nucleus and a horizontal arrangement of fibers. This allows for swelling during what's called imbibition.
Imbibition, like soaking up fluid.
Pretty much. Essentially, the disc soaking up fluid like a sponge when pressure is released, like when you lie down at night. This raises an important point about why water content matters.
Yeah, okay.
Because discs experience diurnal fluctuations, changes in hydration throughout the day. They gain fluid when unloaded, lose it under load. It actually means you're slightly taller in the morning.
Seriously. taller in the morning.
Yep, measurably so for most people.
Mhm.
Then we have Schmorl's nodes. This highlights how delicate the balance can be. What's intriguing here is how disc material, usually the nucleus, can sometimes intrude, push up or down into the end plate itself at areas of weakness.
Ooh, that doesn't sound good.
Well, when this happens, it decreases the end plate's ability to resist the natural swelling of the disc. It weakens it. And potentially, it could be a precursor to failure of the end plate and ultimately degeneration of the disc itself. A subtle but significant pathway to potential problems.
Wow. Okay, finally, let's connect all this back to us, the listeners. How do our everyday movements, our postures, even our habits affect these incredible discs, especially in terms of pressure?
Yeah, our daily lives have a profound impact. Simple movements like bending forward, extending backward, side bending, they involve incredibly complex interactions of compression, tension, and torsion within the discs.
Even simple things.
Even simple things. Twisting can produce significant shear forces and torsion. And crucially, increased interdiscal pressure, that's the pressure inside the disc, occurs with a variety of common activities.
Like what?
Think about flexion, bending forward, like reaching for something. Combine that with lifting something heavy. The pressure can skyrocket.
Lifting wrong, basically.
Lifting wrong, or even just lifting heavy. And here's a surprising point from the research. Maintaining poor sitting posture for extended periods.
Like slouching at a desk.
Exactly. Even without lifting anything, that can put more pressure on your lumbar discs than standing upright.
More than standing. Wow.
Yeah, it's a silent stressor many of us face daily. Even everyday actions like coughing or the Valsalva maneuver,
Right.
like holding your breath and bearing down, maybe straining.
Oh, yeah.
Even that can significantly elevate this internal disc pressure. So what seems like a simple, normal action can actually be a tiny stress test for your spine. Understanding this can really empower you to make small but significant changes in your daily routine.
Wow, what an incredible journey through the intricate world of our spine's supporting cast.
Mhm.
From the multi-layered, force-transmitting fascia connecting everything, to the precisely targeted muscles, the strong, elastic ligaments, and those dynamic, load-distributing discs. It really is a profound testament to the complex and integrated design of our bodies. That suspension bridge idea feels right.
Absolutely. What we've really seen today is that every single component, from those crisscrossing fibers of the thoracolumbar fascia connecting the whole body, to the subtle bulging of a disc under pressure, every bit serves a vital purpose, enabling movement, maintaining stability.
It's a beautifully engineered system.
It really is.
Oh.
Where every part supports and influences the others, it creates this symphony of motion and resilience that, yeah, we often just take for granted.
So what does this all mean for you, our listener? We genuinely hope you'll never look at your back the same way again, knowing the amazing work it's doing behind the scenes.
Yeah, and this maybe raises an important question for you to consider. Knowing how intricately connected and balanced these structures are, and how movements and daily habits impact them. How might understanding concepts like the hydraulic amplifier effect of the fascia or the mechanics of increased intradiscal pressure on your discs, how might that change the way you approach your posture, or your movements, or even just how you sit at your desk every day? What small changes might you make to better support this incredible engineering masterpiece you carry around?
A truly thought-provoking question to mull over. It's really makes you appreciate the incredible dynamic machine we inhabit every day. Thanks for joining us on this deep dive.